first question is page 362, number 10. And here we've got a 10 kilogram block lying on a smooth ramp that's inclined at 30 degrees. What force parallel to the ramp would prevent the block from moving? Assume that 1 kilogram is 9.8 newtons. So here, basically what we want to do is take a look at what would be the amount of the force, the magnitude of force of gravity that's going along the ramp, parallel to the ramp. So this is going to be very similar to what we did. So the magnitude of the force of gravity is 10 times 9.8, of course, so 98 newtons. And that we're going to have two forces that are acting at a 90-degree angle. One is parallel to the ramp and one's perpendicular. So those forces represent how much of the force of gravity is working parallel to the ramp and how much is working perpendicular. So what we want to find is the magnitude of force 1. And to do that, we're going to need to figure out the angles in here. So I know that that's 30. I also know that gravity is perpendicular to the ground. So then I would know that this angle up here is 60 and that that's going to be the same as the 60 degrees in there because those two angles are definitely the same. That's an F pattern there. So I could say that the magnitude of F1, if I want to kind of draw that out, that's 60 degrees. So I could say the magnitude of F1 over 98 is cos of 60. And then the magnitude of F1 is going to be 49 newtons. Now that's how much of the force of gravity is going parallel to the ramp going down the ramp. So we would need an equal force, an equilibrium force going up, but the magnitudes of those would be the same. So you would need a force of 49 newtons up the ramp to prevent movement. And that would probably be the force of friction, we would assume, on the ramp, but it might not be. It also could be maybe there's a rope tied to the block, like holding it up. Maybe there's a tension force in a rope. So whatever it was, there would be some kind of force, that blue arrow going up the ramp, that would counterbalance and be an equilibrium to the force of gravity that's working parallel to the ramp. Okay. Next one. Oh, this one tends to throw people off a little bit. I think it's B that is really the problem here. So if we have three forces that each have a magnitude of 1 Newton, they're arranged to produce equilibrium. So if we've got three forces, I'm going to draw them. If they all have equal magnitudes, then remember that three forces that are in equilibrium form a triangle. They balance each other out and that they would add up to 0. So all of those forces balance each other up and there's no net force. So if this is true, if we've got this situation where we've got all three of these forces going into a triangle and all of their magnitudes are equal, then we would know that this is an equilateral triangle, right? If you have a triangle and all three sides are 1, then you know that that triangle would have angles of 60 degrees inside the triangle. Now, the angle between the vectors, so the angle between is always tail to tail. So if I was to draw these vectors, I'm going to try and kind of keep their orientation correct. If I'm going to draw these tail to tail, then F2 would kind of transfer to go down there, and F3 would go out that way. And now, what would the angle be between those vectors? F3 somehow looks way shorter than the other ones. So here, we could look at this. Maybe you just look and say, oh, well, like they're all equal, and their angles between them would be equal, and they form a circle, so it's 360 divided by 3. Or maybe you look at it and say, just like we did with adding vectors, oh, hey, adding them head to tail was 60, so that this makes a C pattern. Whatever way you do that, that would be 120 degrees between the vectors when they're all tail to tail. And then the next one is on the velocities homework page. So we're on to page 369, number 7. And this says an airplane heading due north at 800 kilometers an hour when it encounters a wind from the northeast. So from means that's where the wind is coming from, but it's going towards the southwest. So if I have wind and it's coming from the northeast, that means it's going towards the southwest. So my wind velocity is not going to northeast. That's a common kind of misconception there. So here we've got our plane traveling directly north. And then the wind is coming from the northeast, which means it's going towards the southwest. And we want to figure out what is the resultant vector. Remember, plane plus wind equals the resultant. So here I would know that this angle in here, so the plane is going directly north, the wind is going southwest, so that this angle up there is 45 degrees. So then I'm going to find the magnitude of my resultant, which will be 800 squared plus 100 squared minus 2 times 800 times 100 times cos 45. And put that all into your calculator. So I get that my resultant would be 732.71 kilometers per hour. Now, that's not a velocity. That's just a speed. If they ask you for velocity, you have to remember, hey, velocity is a vector, needs two parts. I also need my angle. So I'm going to look at where those vectors are tail to tail and find that angle. Now, because this is a velocity, I don't want you to tell me, oh, it's this many degrees from vector P towards vector W. Good form here, we've got a compass. You know where north, south, east, and west is. Tell me what direction on that compass you're actually going for your resultant velocity. So here, the wind is definitely the smallest, so I'm not going to have an ambiguous case. So I will have sine theta over 100 equals sine 45 over 732.71. So here I get that this angle is really little. That's going to be 5.54 degrees. So writing a summary statement, therefore the resultant velocity is 732.71 kilometers per hour, and my direction will be north 5.54 degrees west. Part B says, how far will the plane travel in 1 hour? Well, we have the velocity in kilometers per hour, so just that 732 will be how far it goes. Okay, I'm just going to switch over the meat. Any questions here? Okay, guess not. So the next one, question number 4 here, page 364, number 17. Oh, this is a little bit out of order. This is back to the previous section. Normally I try and sort these, but I must have missed it. So here we've got very, very similar to the tension question we did in class. We have 2 strings holding something that is putting a force of gravity downwards, but we don't have the angles. So the difference here is that we're going to have to figure out that the angles just using the cosine law here. So we can like label A and B. So I know that 24 squared equals 32 squared plus 40 squared minus 2 times 32 times 40 cos A. And similarly, for angle B, I could say 32 squared equals 24 squared plus 40 squared minus 2 times 24 times 40 cos B. And then we're going to figure out what our angle A and what our angle B are equal to. So angle A, I get that would be 36.87 degrees. And angle B, I feel like I already did this and I remember them. Angle B, I get 15.13 degrees, 53.13. So now this question is basically equivalent to what we did in the lesson. And I'm going to kind of redraw this and really try and just forget about those lengths, because now I think that the lengths can mix people up. Because now we want to think about forces, not the actual lengths of the ropes or strings or whatever we have. So now we want to think about our forces in here. And we know we've got the force of gravity going down, and that the magnitude of that would be 5 times 9.8, which is 49 newtons going down. And I also have I think in the lesson I called this F1 and F2, but then I think in the notes I said T1 for tension. It doesn't matter, whatever notation you want to use there. So here I know that they have to have a resultant that is the equilibrant of gravity. So what I need to do here is to figure out what some angles are. So I would know that this angle in here, if I make this a 90, that this is going to be 36.87, and making this a 90, this is going to be 53.13. And I actually sort of hate this question in the textbook because this angle here ends up in this case being a 90-degree angle. But that's almost never true in these tension questions. And it's so kind of like weird that it does end up as a 90, that sometimes people see this one situation of this question and say, oh, that bottom angle's always 90, and it's not always 90. It's usually not 90. So I'm going to very much avoid kind of even, I'm going to try not to notice that that's a 90-degree angle, quite frankly. So I would look at this and say, oh, hey, look, this is like a Z pattern there, and that this angle up here is, that's not a pen, 36.87. And then I'd say, and I also know this angle in here, because it's the same as that one, that's 53.13. And then I could find, and I would have to subtract and figure out that that was 90. So now I've got this question where I have the resultant, which is 49, and here's this 36.87, and there's 90, but only because I subtracted, not because 90 is special, and there's 53.13, and there's the magnitude of F2, and there's the magnitude of F1. So now I'm just going to use sine law to figure out what those two magnitudes are. So the magnitude of F1, and again, I could use SOHCAHTOA because I know that this is a 90-degree triangle, but it's not usually. So I'm using sine law because I don't want you to generalize that because it's usually not true. So magnitude of F1 over sine of 36.87 is 49. Got some extra random equal signs in there. 49 over sine 90. And the magnitude of F1 is going to be 29.4 newtons. And then I'll do the same for F2 over sine of 53.13. And there I get 39.2 newtons. So determine the tension in each string. So the tension in the F1 was in the 32 centimeter string. I believe, yeah. So therefore the tensions are 29.4 newtons and 39.2 newtons in the strings. Remember that for tension, we do not need to reference an actual angle or direction because the tension is given the direction of the string that you're measuring it with. Just pop over and check for questions. Okay. All right. Here we go, page 369, number 4. Adam can swim at a rate of 2 kilometers per hour in still water. At what angle to the bank of a river must he head if he wants to swim directly across the river and the current moves at 1 kilometer per hour? Okay, so here, let's draw a river. And I'm going to draw our current flowing left to right, just because I always draw it going left to right. So we know that just like the plane plus the wind equals a resultant, we know that his swimming plus the current will equal the resultant. And we're told that he wants to swim directly across the river. So he needs to go this way, that he wants his resultant to go straight across. So he has to start swimming a little bit this way so that the current, when it pushes him, will end up going straight across. Okay, so we know that the magnitude of his swimming velocity is 2. The magnitude of the current is 1. So I'm going to take a look at this triangle here. I don't know the magnitude of the resultant, but I know that the 2 is going to be on the hypotenuse. The 1 is going to be across. So I'm just going to solve for that angle theta, and that's sine. I do know that this is 90 because it says that he wants to go straight across, so we know that that's perpendicular to the current. So sine theta is 1/2. That means theta is 30 degrees. But it says at what angle to the bank. So what we're actually looking for is the outside angle. I still think it's easier to do what I just did and then just subtract it. So I'd say from the bank, the angle is 60 degrees. So remember that from the bank means from the edge of the river. So we found the angle that he had to move from perpendicular. We wanted the angle of the bank, so just subtract that from 90. Okay, the next one, they're swimming again. Judy and her friend Helen. They live on opposite sides of a river that's 1 kilometer wide. Helen lives 2 kilometers downstream from Judy on the opposite side of the river. Okay. So here we go. Helen lives 2 kilometers downstream. So here's Judy, and Helen is down here, and that's 2 kilometers. And the river is 1 kilometer wide. And Judy can swim at a rate of 3 kilometers per hour. So the magnitude of Judy's swimming is 3. And this is a super fast river. The current is faster than she's swimming. It is 4 kilometers per hour. So Judy swims from her cottage directly across the river. What is her resultant velocity? So she's starting out swimming like this. She says, I'm just going to aim right across the river and see what happens. But we've got the current, which is going to be pushing her downstream. And then we want to figure out what's that resultant going to be. Okay, so this is kind of nice because we do know that we've got a 90-degree angle there. So I have a nice right-angled triangle. I know that her swimming amount is 3 and the current is 4. So we can find the magnitude of the resultant. So just Pythagorean theorem. The magnitude of the resultant is 5 kilometers per hour. But we want resultant velocity. So we have to figure out what the angle is as well. So I'm going to put in that theta and say that tan theta is equal to 4/3 and find the angle. So I get that she's going at an angle of 53.13 degrees downstream. Okay, so her velocity is 5 kilometers per hour, 53.13 degrees downstream. So part B says, how far will she be from Helen's cottage when she reaches the other side? So if she travels along this resultant path, will she land at the other side before Helen's cottage, after Helen's cottage, or right at the cottage? We don't know. We have to figure this out. Now looking at the distances. So this is velocity. Make sure you keep your units the same. Now I'm going to look at distance. I might even spell distance correctly. So now I'm going to look at the distance of this. So I know that this is 1 kilometer wide. So I'm going to put in an X there. And I also know that this direction she's going is 53.13. So I could say that X over 1 is tan 53.13. So here I get 1.33 repeated kilometers. So that's how far down she's going to be. So she still will need to walk a ways. So she'll have to walk 0.67 kilometers. So she'll land like here at 1.3 and she'll have to walk a little bit further. Okay. Question in there, Max?
Yeah, I have a question. Why can't we just make that triangle into like just a full distance triangle? Have one side be the 2 kilometers, that is the distance between their houses on the bank, and the 1 kilometer across the river.
Oh, because she's not swimming and going directly to the cottage, we figured out the angle that she was going from the previous one. So we're looking at like that angle that we found in terms of what direction she was going to swim, that her resultant would be. And she's not going to wind up right at her friend's cottage.
Okay.
Okay.
Makes more sense.
Yeah. So then the last one, I'm going to need to like squeeze another slide in here because I'm running out of space. The last piece says, how long would it take her to reach the other side? So we know that her resultant velocity the magnitude of her resultant is 5 kilometers per hour. And what's the actual distance that she's swimming? So we know that this is 1 kilometer. And this will be like the distance that she actually swims. And we know that this is 53.13 degrees. So we want to figure out what that distance would be so that we can find out how long this would take. So here we've got cos 53.13 is 1 over the distance she swims. So 1 divided by cos there. She ends up swimming 1.67, like it's repeated, kilometers. So her distance is 1.67 kilometers. Her speed is 5 kilometers per hour. So we know, like in, I don't know what science you guys do that in, but the amount of time is the distance, so 1.67 divided by 5. So it'll take her a third of an hour, or 20 minutes, to get across to the other side. Okay, more velocity ones. We've got an airplane. Oh, I like this one. This is one of the ones I mentioned about working backwards. So I know that the resultant is equal to the plane's velocity plus the wind's velocity. So let's take a look. An airplane is traveling north 60 degrees east, and this is going to be resultant, with a resultant ground speed of 205. So the magnitude of the resultant is 205. The nose of the plane is actually pointing east with an airspeed of 212. So the plane is actually going straight east. And we want to figure out what is the wind. How much is the wind pushing it? So I know that I have to draw the plane plus the wind. So the wind is, remember, adding vectors like head to tail to figure that out. So working through this, I need to figure some stuff out. I know the magnitude of the plane and the magnitude of the resultant. I'm told that this is 60. So I know that the angle inside that triangle will be 30. So if I'm looking for the magnitude, I'm going to find the wind speed first. So the magnitude of the wind, this is going to be cosine law. So I've got 205 squared plus 212 squared minus 2 times 205 times 212 times cos 30. Okay, so I get that the magnitude of the wind is going to be 108.14 kilometers per hour. Then I want to figure out from here what the direction of the wind is. I don't know why they asked this kind of in the backwards order of what they normally would. But I'm going to put theta in there. And this is a little, I don't know, like it's not a great situation in terms of figuring out what the wind is, but I know I want to figure out the wind direction. So I know I need to know an angle at the tail of the wind. So that's why I'm putting my theta there. Now, really be careful because this one looks like it maybe could be an ambiguous case. And we have to really think about, could this angle be bigger than 90 degrees? And if you're unsure, always use the cosine law. So here I know that the plane has a bigger magnitude. So that's the biggest side. It's going to be across from the biggest angle. If I have an obtuse angle in this triangle, it's actually going to be this one. So I don't have an ambiguous case there. So I could say that sine theta over the resultant, which is 205, equals sine 30 over 108.14, and then we'll figure out what that angle is. And I may really have not drawn this to scale, So don't get too attached to your diagrams. Because here I get, oh, I guess it's not too bad. I get that theta is 71.41 degrees. So now we need to kind of think about what does that mean about the direction of the wind in terms of a compass. So I'm going to take the start of the wind and redraw a compass there, like a north, south, east, west. What does that mean? So if this is north, I know the plane was straight east. The blue plane vector was straight east. So if I know this angle in here is 71, I'm going to subtract that from 90 to figure out the angle, because I always want to state angles as starting at north or south. So that's 18.59. So I'd say, therefore, the wind velocity is 108.14 kilometers per hour. And then your direction, it will be north 18.59 degrees west. If you have actual directions in your question, you need to use them in your answer. So you may need to kind of figure out some calculations to reference those properly using the coordinates like north, south, east, west. Flipping over. Everybody okay? All right. One more. We've got a canoe. Mary leaves a dock, paddling her canoe at 3 meters per second. She heads downstream at an angle of 30 degrees to the current, which is flowing at 4 meters per second. Okay, that's a lot of stuff. Let's draw the river. So the boat speed is 3 meters per second. And the current speed is 4 meters per second. And we're going to be figuring out the resultant. We're not even really asked for the resultant, but we're going to need to know some stuff about this. Okay. So she's paddling her canoe at 3 meters per second, and she's heading downstream at an angle of 30 degrees to the current. So I know current is going that way. So the boat is heading this way at this 30-degree angle. So there's my boat velocity. And then the current is going to be going more down that way. And then I'm going to draw in my resultant. So the resultant is going to go there. So we need to look at the C pattern like we've done before and notice that that angle up top will be 150 degrees. So we want to know what's the magnitude of the resultant. And that's going to be cosine law. So we've got 3 squared plus 4 squared minus 2 times 3 times 4 times cos 150. So that comes to 6.77 meters per second. And then I'm also going to want to figure out my angle, like what angle in, basically in there, is this going to be? Okay. So here we can do sine law. So I'm going to go over here. Sine theta over the magnitude of the current is 4 equals sine of 150 over 6.77. And we'll figure out our theta. So 4 times sine 150 divided by 6.77 and inverse sine. So the angle there I get is 17.18 degrees. So that gives me my resultant velocity, but I'm not actually even asked my resultant velocity. What I am going to want to know is that it's asking me some things about downstream. So downstream is like this direction. And then it also asks me about like getting across the river, which is like that direction. So what I'm actually going to do is break apart my resultant velocity and figure out how much of that velocity is going downstream and how much of that velocity is going across. So if this is my resultant, I'm going to call this V1 and V2 because I'm going to want to break this apart into how much of my velocity is going down the river and how much is getting me across the river. So I'm going to want an angle in here in this triangle. And are we all okay if I say, well, this theta was 17.18 and the whole angle here was 30. So I can subtract from 30 and get this angle between the resultant and the bank. Let me know if that doesn't make sense to you, but I hope that it does, because that would be 12.82 degrees. And the magnitude of the resultant I figured out was 6.77. So from here, I'm going to figure out the magnitude of V1, because V1 over 6.77 is cos of 12.82. And that gets me that I'm going 6.6 meters per second downstream. And then I'll do the same for V2 because the magnitude of V2 over 6.77 is sine of 12.82. So figuring that out, I get 1.5 meters per second going perpendicular to the bank. So I'm going to need to add into this, because the first question, adding on a slide here, so how far downstream in 10 seconds? So I found that this V1, which is the amount that I'm going downstream, so this V1 here is 6.6. So I would say the distance is 6.6 meters per second times 10 seconds. So you would go 66 meters downstream in 10 seconds. And then question B said, what is the length of time required to cross the river if it's 150 meters? So we know that the distance is 150 meters and my speed, my velocity going across, is 1.5 meters per second. So how long will that take? So the time is the distance divided by the speed, So it would take you 100 seconds to cross. Okay, so it doesn't even ask for the resultant, but you do need all of the information from that resultant to be able to solve for the pieces that it's asking for. So you have to kind of recognize that the resultant itself is a middle step, because what we're looking for is how far are you actually going downstream and how far are you actually, or how fast are you actually going across. And both of those things come from finding that resultant.